In November 1971, according to Intel's official company archives, a small team of engineers released something that would change the world, the Intel 4004, widely documented as the first commercially available microprocessor. This chip, no larger than a thumbnail, contained 2,300 transistors, a fact confirmed by the original technical specifications published at the time. Before this moment, computers were room-sized machines accessible only to governments and large corporations. The microprocessor would democratize computing, though few observers predicted this outcome in 1971. To understand the microprocessor, we must first examine its building block, the transistor. According to Bell Labs historical records, William Shockley, John Bardeen, and Walter Brattain demonstrated the first working transistor in December 1947. The trio received the Nobel Prize in Physics in 1956 for this invention, as documented by the Nobel Foundation. A transistor acts as an electronic switch, turning current on or off, or as an amplifier. These two functions, switching and amplifying, form the basis of all digital logic, as explained in foundational electrical engineering textbooks. The next critical step, according to engineering historians, came in 1958 when Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed the integrated circuit, a method of placing multiple transistors on a single piece of silicon. Both men filed patents within months of each other, a fact documented in U.S. Patent Office records. Kilby received the Nobel Prize in Physics in 2000 for his contribution, though Noyce had passed away by then and Nobel Prizes are not awarded posthumously. The integrated circuit allowed dozens, then hundreds, of transistors to work together on one chip. In 1965, Gordon Moore, then at Fairchild Semiconductor, published an observation in Electronics magazine that would become legendary. According to the original article, Moore predicted that the number of transistors on an integrated circuit would double approximately every year. He later revised this to every 2 years, as documented in subsequent Intel publications. This prediction, dubbed Moore's Law by colleagues, proved remarkably accurate for decades. It's important to note that Moore's Law is not a physical law but an observation about the pace of innovation in semiconductor manufacturing, a distinction Moore himself emphasized in later interviews. The Intel 4004 emerged from an unlikely project, according to Intel's corporate history. A Japanese calculator company, Bizicom, commissioned Intel to design chips for its calculators. Engineer Federico Fagan, along with Ted Hoff and Stanley Mazur, designed a general-purpose processor instead of calculator-specific circuits, a crucial decision documented in their patent filings. The 4004 operated at 740 kHz and could execute 60,000 operations per second, figures confirmed in the original datasheets. It processed data in 4-bit chunks, meaning it could work with numbers from 0 to 15 at a time. This seems primitive today, but it represented a fundamental shift in computing architecture. The microprocessor's real impact became clear in the mid-1970s when hobbyists and entrepreneurs began building personal computers. The Altair 8800, released in January 1975 according to Popular Electronics magazine, used Intel's 8080 processor and is widely credited as the first commercially successful personal computer. According to historical accounts, it sold thousands of units to enthusiasts. Then in 1977, as documented in product launch records, the Apple II, Commodore PET, and Tandy TRS-80 brought computers into homes and small businesses. Each relied on microprocessors to deliver computing power at a fraction of the cost of traditional systems. In 1978, Intel released the 8086 processor, which according to Intel's technical documentation introduced the x86 instruction set architecture. This architecture would dominate personal computing for decades. When IBM selected Intel's 8088, a variant of the 8086, for its IBM PC in 1981, as confirmed in IBM's product announcements, the x86 architecture became the de facto standard. Industry analysts have documented that this single decision shaped the competitive landscape of computing. The x86 architecture remains relevant today, though it has evolved through numerous generations, a longevity few predicted in the early 1980s. By the 2000s, according to semiconductor industry reports, microprocessors had evolved from thousands to billions of transistors. Intel's Itanium 2 processor, released in 2003, contained 410 million transistors according to Intel's specifications. AMD's first processor to exceed 1 billion transistors came in 2008 with certain models, as documented in product literature. Modern processors, according to recent technical specifications from manufacturers, can contain tens of billions of transistors. These transistors, measured in nanometers, billionths of a meter, enable the smartphones, laptops, and data centers that power contemporary digital life. The density more observed has increased by factors most observers in 1965 would have considered impossible. Today, according to market research firms, billions of microprocessors are manufactured annually, embedded in everything from cars to refrigerators to medical devices. The fundamental architecture, transistors organized into logic gates, processing instructions in sequence, remains remarkably similar to those early Intel designs, as computer science textbooks confirm. However, researchers note that Moore's law is slowing as physical limits of silicon are approached. Industry reports indicate that companies are exploring alternative materials, three-dimensional chip designs, and quantum computing. The microprocessor revolution that began in 1971 continues, though its next chapter may look very different from its first 50 years.